hit record. Okay, so this is the Blackbody radiation apparatus. At this end is the lamp, and you can see wires going into it to provide voltage, and then another two wires that are going to go into this current sensor. So you're actually going to be able to measure the voltage and the current on the filament, and then that current sensor has an output that's going to go into the data collection in the computer. So this lamp is going to, once you know voltage over current, that gives you the resistance of that filament inside that lamp there. And of course, that's going to give you the temperature based on your formula in your write-up. And you can see some collimating slits there to adjust the width of the beam. And the beam's going to go through here. There's a lens right here, a converging lens to collimate the beam. And that beam's going to extend this way and go through that prism. And as you know from studying, that the different wavelengths will get bent through the prism at a different angle according to the formula that you were given by Dr. Essergen in your lab manual. So that's a triangular prism. Let me come over here a little bit so you can see it a little differently. From another angle, I'll get up above. If I look down on it, it's actually a triangular prism. That black piece is in the way a little bit, but you can basically see it. And then when each wavelength will get bent differently, and then go through another converging lens to collimate the beam. You know, the beam's always trying to spread, so you're still always trying to collimate. And it's going to go through there's a little wheel here. And that wheel will adjust the width of the beam that gets through. And it's going to go in this optical sensor. Now, that optical sensor looks like a black box, and indeed it is. And inside it is basically a chunk of material that when photons hit it, they kick out, a current. And then that optical sensor has an output signature voltage current, like any electrical signal. And it's going to go into the computer here. And so the thing is that when the light comes through, now, as we move this here, we're going to be able to see different wavelengths coming in here. Now, as you can see, when I move that, the prism also rotates, so that's going to be a source of systematic error. That's going to be locked down so that when I move this, the prism stays in place. But it's interesting, the equipment's sitting here. It's not set up yet, but you can see that if I move that and the prism moves, that's going to create systematic error, right? Dr. Essergen made that a point in his lab manual that you hopefully have all read at this time, or will read before now and actually doing this experiment. So it's really elegant because the light's coming out from a black body, that's the filament, and you've got a measurement on the temperature because of the resistance. And then the light's coming through, and you're actually measuring the wavelength because the different wavelengths get bent by the prism at different angles. And so as you move this thing here to different angles, you're actually going to measure the light hitting the sensor at a specific wavelength. And again, you have a formula for the light hitting a prism and coming out at the angle it comes out, what its wavelength is in your lab write-up. We're not here to do theory. That's done for you. And also the appendix of Dr. Essergen's write-up, which I thought was actually very complete. So you have all that, students. So anyways, this black box again, that cross-sectional area of that light hitting the sensor is critical because the sensor is going to measure energy per second, and then of course energy per second per area is the intensity at a specific wavelength. And if you'll look at the Blackbody radiation curve, that intensity is your vertical axis as a function of wavelength. And you're actually, this experiment is actually going to, as you rotate this to the different angles, you're picking off that intensity at the specific wavelength from the black body inside there, inside that filament, which is actually quite extraordinary. It's a very historic experiment, and I think this apparatus is really boss. So anyways, after you collect the data of that intensity at each wavelength, you know, the angle of this gives you the wavelength. That corresponds to a specific wavelength. And of course, the output of this black box here, the optical sensor, gives you that intensity. That's going to go into the computer here. And of course, the computer is basically a voltmeter, so don't be scared of it. And of course, the signals come in, and there's software that's going to take it and make the curve for you. But anyways, that's the application.
I will tell you a few of the subtle points in this experiment. The first thing is, let's start from the right side, is the collimating slit. The collimating slit needs to be exactly aligned with the filament, and the filament needs to be vertical, and the collimating slit needs to be aligned. So what you do, you just look here, and then you align it with the filament so that you get the most light. If you don't get enough light, then you're not going to have a good data. The next thing is this focusing lens. Actually, this is not focusing lens, collimating lens. It needs to be exactly 10 centimeters from the collimating slit. So the collimating slit is right now at 8 centimeters, so you need to put this on the mark, which is 18 centimeters right here. Okay, so now it's exactly 10 centimeters. The next thing is, so when this apparatus aligns at 0 degrees, you want your prism to face exactly in line with the light. So the apex of the prism needs to face exact line. So you want this to be exactly at 0 line. See, this thing in principle rotates. So what you do, oops, it rotated too much. There is a thumb screw or a wing nut at the bottom, and then you turn this wing nut, you tighten it while this thing is exactly aligned, okay? So you just tighten it, and then you later check it that it doesn't rotate. Another problem with this thing is there needs to be a gap between the prism and the apparatus, otherwise it's going to keep turning. So I just increase the gap by loosening it. And after I loosen it, I tighten it again.
So that's actually on a screw, and as you turn the screw, the prism raised up. Is that right?
Exactly.
So that it doesn't catch on the table here when you spin the table, because if you spin the table and the prism catches, this prism spins with it, and that's your systematic error.
And there's a locking wing nut at the bottom.
I see. Okay.
Okay, so there's that. So now it seems okay. And then another problem here, sometimes the screws on this rotary motion sensor are loose. So these two screws, so you want to make sure they are tight.
Oh, so that's a black box that measures the angle.
Exactly.
Oh, and I didn't mention that. Thank you.
And another problem is this little screw might be sometimes loose too. And it was loose actually. So.
Oh, that black screw, that's a set screw.
It's that set screw holds the pinion. It's the pinion attachment there.
Gotcha.
So it needs to be tight, otherwise the pinion is going to keep slipping, right?
Right.
And another possibility is this pinion sometimes slips on the disc here. It doesn't catch with it. So you want to make sure it doesn't slip. If it slips, then you need to wipe off any oil on the disc. It needs to really completely clean.
Okay.
Otherwise, it's going to basically, there's not going to be enough friction to have this pinion basically keep track of the disc. It will keep slipping.
Right.
So you don't want it to slip. And the final thing here, this focusing length needs to be exactly in this rectangular box. Okay. So I just put it in that rectangular box there.
Okay.
Painted.
I see.
Mm-hmm.
I see.
So. And then these are, let's see, these are broad spectrum light sensor, the black box.
Okay.
And then you want to set the gain according to the what's set in the manual here. If the gain is too large, then the signal is going to saturate. Then you want to lower the gain if that happens.
Okay, when you say broad spectrum, that means it's going to measure power.
It goes from infrared to, I think, UVA.
So say 280 nanometer.
Say from like something like around probably around 200 nanometers to several thousand
infrared nanometers.
Yeah.
And so that's a pretty sophisticated sensor so that it can measure power even over many wavelengths and still give you a good number.
Yeah.
That's a pretty good piece of electronics in that black box at the end there.
So if everything goes well, you'll get some decent data. If it doesn't, then we want to see what's going wrong.
You would come in and fiddle with it, and try and see where you're getting your errors.
Yeah, this one is actually among the 153 labs. This one is probably the most complicated one. So, I mean. There's usually some subtle thing which might not be set up correctly, and then it doesn't work. So in that sense, it's probably the most complicated experiment in 153. But overall, the idea is pretty simple. So and it works if everything's set up correctly. So
great. Okay, thanks. Okay, here we have cable inputs. We have the yellow and black right here for the rotary motion sensor. Then A is the broad spectrum light sensor, B is the voltage on the filament, C is going to be the current on the filament. And that's going into this Pasco box here, which then has an output cable that loops around into the computer. And the software is, of course, talks to this black box, blocks as output. Now, I want to show you this little knob there, right there. See that little cylinder? As that spins, it rotates the table, and there's a rotary motion sensor inside that black box, and that's going to tell you the angle that your light sensor is sitting at here as it swings through the rainbow of colors coming out of this light filament. So the cable connections are pretty clear here. You've got rotary motion sensors, 2 cables, and then broad spectrum voltage and current. Broad spectrum light sensor, voltage and current, and then you have to type in the numbers into the computer so that the software is calibrated.
Here I'm going to show you how to set up the calculator in the app. Basically, the program here that we are using, which is Capstone, in the lab manual it's Data Studio, but Capstone is a newer version which replaces Data Studio. Basically, you gather data using the sensors, such as the light intensity, voltage, etc. And one thing you can do in Capstone is actually to calculate different quantities using this data. For example, I define here as theta as the pinion angle divided by 59.69. So basically, pinion angle is the angle of the rotary motion sensor, and then I divide it by 59.69 to actually calculate the true angle, because the rotary motion sensor is connected to the disc through a pinion, and the pinion angle here is defined as, you can see that it's the actual angle of the rotary motion sensor, which is connected to the channel P1.
Let me make a comment right there. And if we look at over here, when Dr. Ergen is talking about, you can see this rotary motion sensor. As I rotate the optical sensor, you can see the the rotary, see that little pinion rubbing on the edge of the disc is spinning.
And 59.69 is the ratio between the number of rotations of the pinion to the rotations of the large disc.
That's right. So the little, see that bolt going around, as that goes, that's got to go around 59 times in order for the big disc to rotate once.
59.69 times.
59.69 times. Good.
All right. So basically, and then as you see, we define the V as the voltage sensor connected to channel B, and then the current I, we define it as the current sensor connected to channel C. And then we type in the formulas in the manual, such as the refraction index N being equal to the formula in your manual. So the refraction angle is defined in terms of or calculated in terms of the angles. And theta 0 is an angle that you need to input during the experiment. It's the angle of the central peak. And then likewise, we define the wavelength lambda in terms of the index of refraction. It's actually not defined but calculated. So, and then we also calculate the temperature of the filament or temperature of the black body in terms of the voltage and current through the filament basically. So these are all the calculations that we need. Once we have these calculations, we can plot those on the graphs in capstone. For example, here I'm calculating light intensity as a function of the angle here. And here I'm calculating the temperature of the filament as a function of time.
Where are you?
Right here.
Oh, this one. Sorry. Temperature of the filament is a function of time.
Yeah.
Pretty constant, right?
Right, it's pretty constant around 2418
Kelvin. Yeah, okay.
And finally here...
This is the golden graph, right?
Right, so this is the Planck curve. The Planck curve, which is the intensity versus the wavelength. Here on the above curve, we get the intensity versus angle. And we are able to convert angle to the wavelength using formulas in the manual. That's it.
Okay, we're going to turn the voltage on here. So that the voltage on the filament is 6 volts, and as you know from your manual, that's going to give you a specific temperature, right?
Let me see where we start from.
That's about 6 volts there. And then over here, you can see in here the filament is the light's coming through that slit, and the light's going to travel, and you'll see this little rainbow there. See that rainbow? We're gonna move our sensor through the rainbow, and that's going to give you your black body spectrum, right? And then the 0 point he's talking about is the straightaway, the central peak right there, when your sensor goes through that central peak right there. So that's what Dr. Essergen is talking about when he talks about this, the central peak. But you can see this rainbow right here. Those are the rainbow, the light coming from the filament split into all the different colors by the prism, and the sensor is going to measure intensity of each little wavelength. And then what we'll do is we'll sit here as you see that sensor goes, the rainbow go through the sensor, we'll be able to see the graph, the black body graph plotted on that computer screen in the back there. Action.
Here is how we take data here. The first thing you need to do, you put your hand between the light source and the lens here and then tear the light sensor. So that basically, that's supposed to tear the 0 of the light sensor. So when there is no light, you want the light sensor to show 0. And then now we click the record button, and then you will see the data on the screen, and then we slowly rotate this. And I'm plotting two different things. One thing is the light intensity versus angle, and the other one is light intensity versus the wavelength.
And now you can see the rainbow is going to go through the sensor here, and you'll see the data respond there. See that rainbow of light below hitting the sensor? That's this right here, that rainbow.
On the right, you can see the Planck curve, which is looking very nice. And then we need to scan through the central peak for calibration purposes. Central peak is
Central peak is coming up. Keep going, keep going, keep going, keep going. Here's the light. The central peak you see is going to hit the sensor. Keep going. Hitting the sensor right about there and go through it. Keep going. Okay.
So I think we passed central peak, right?
Yes, sir.
So now we can see the central peak actually here on the graph, right here. So we need the position of that for calibration purposes. And on the right side, you are seeing the Planck curve as a function of lambda. So this concludes the data taking process for the by the way, the voltage here right now is 9 volts. So that's the highest temperature for the filament we are doing. And next we are going to do 8, 7, and 6 volts, but we are not going to have a video for those. But those data runs are going to be included for your analysis.
Okay, hang on one second now. Well, I'm going to leave that there. I'm going to bring them over here and show them a better view of the Planck curve that we just generated, that Dr. Essergen just generated by taking the data. And that may look something like what you have seen in your textbook.
And let's do the 8 volt run quickly here, Doug.
Okay.
For comparison purposes.
And this is intensity versus angle there.
So I'm going to now change the voltage to 8 volts.
Hang on, let me get your hand in focus there. Okay, go ahead. So you're now changing the voltage on the filament, which changes the current, which then will change the temperature of the filament. Good job.
So now we are going to, by the way, every time we start a new run, we need to start from the stop point on the apparatus. So I turn it all the way to the stop, and then from the stop we start scanning. So now, and let's not forget to tear the sensor first. I put my hand blocking the light and I'm tearing it. Now I'm going to start a new run. Are you filming it, Doug?
I am, yeah. Rainbow's going through the sensor now. And you can see that data start to jump as the sensor starts to see light at the different wavelengths. And the rainbow is just about through now. The rainbow went through the sensor, and go ahead and keep going to find your 0 point again, and we should see that spike on the graph on the left to get where theta equals 0 is. I can see it coming up. Keep going, keep going. There's the 0 peak, about to hit the sensor. Keep going, keep going. No, you're not there yet. There it is, right there. And go past it. Go a little past it. Good. Okay, good.
So now we stop recording. And now I'm going to show the both runs simultaneously here if I can. Here. So let's run 1 and run 2.
Oh, hang on. Let me get a close up of that. Is that okay?
Okay.
As you analyze that data, let's go over there. This post is in our way, and that's a beautiful look at that. I mean, that is.
So you can see the darker red here is the lower temperature, and when temperature is lower, two things are happening when temperature is lowered. One, the intensity is getting less. As you can see, the intensity is getting less, and the other thing is the peak is shifting toward higher wavelengths. So when the temperature is lowered, the peak of the Planck curve shifts toward higher wavelengths. Basically, the blackbody temperature is inversely proportional to the wavelength, or it's proportional to the frequency.
So that's Wien's law is that temperature at the peak is a constant over lambda max, right?
Right.
Yeah. And so
Wien's display
yeah.
law, which is mentioned in your lab manual, I think is formula equation number 2. Yes, it's equation number 2. So if you look at that equation, you can see that relation. And then next we are going to do 2 more temperatures, and that's going to conclude our... should we do those quickly, Doug, or...
Yeah, we might as well film it.
Okay, let's
I just want to make a comment. This experiment is basically proving that quantum mechanics exists.
Exactly.
That the energy comes in chunks of h Planck's constant times the frequency. And that's quite extraordinary. That the physics is alive here. It's really an alive thing. I mean, when that light is being measured, the experiment's live, and you're proving that quantum mechanics exists.
Okay, now we are doing 7 volts.
Oh, let me see. Okay, yep, you're at 7 volts for the filament voltage. Hang on one second. Let me mount it back up here.
And I'm going to block the light sensor.
Oh, let me film that so they can see what you're doing.
Okay, I'm just blocking the light sensor like this.
Yeah. And then he zeroes the...
Yeah, with this button here.
Yeah.
And I'm going to do a scan now, if I can. Let's see.
Hang on, let me get set up here. I got to focus. Hang on. 1 second, everybody. Okay, go ahead.
Now you can see all 3 curves at the same time.
Yeah,
nice.
The rainbow is going through the sensor now, and the curve is rising. Beautiful. Do you need to find the central peak again?
Yeah, I mean, it's going to be almost the same, but just in case, it's not going to change much.
Right.
But there's a possibility it might be slightly different.
Here's the central peak almost hitting the sensor, but not quite.
It's coming out around 70 degrees.
Right. There it's going through the sensor. Okay, great. All right, so you got the highest peak is at 9 volts, then 8 and 7.
And then we'll do 1 more temperature now, which is 6 volts.
Okay, let me see what you got there. Hang on 1 second. I can't see it. Hang on. Okay, go ahead. Beautiful, 6 volts. And then here we go for another data run.
Show you our final run.
Hang on, let me focus camera. 1 second, doctor.
Okay, so I'm gonna tear it. Now I'm gonna do the final run here.
Okay, go ahead. Rainbow's coming up to the sensor.
Trying to go slow for precise data collection.
Yeah, there's the going through the sensor. Here's your 6 volt graph coming up. Beautiful. Sorry about that post in the middle of the screen where it's actually holding everything in place, so we can't move it. But I'll come back to the screen close up again when he's done. Coming to the central peak again. Central peak. There you go. Coming right there. Right about 70 degrees again, 69?
Yes.
Okay. Now I'm gonna come up and look at both I would like to look at the black body curves.
And if you could,
yeah.
could you focus on this screen?
Of course, I've come up here. Hang on one second.
So I'm zooming here on central peak on the light intensity versus theta graph. Zooming.
Yeah.
And then after I zoom it,
Yeah.
and I'm going to use this tool here, which is the, I believe it's this one. It's the coordinates tool.
Okay.
To just measure the coordinate of the central peak. It's showing 7.14 degrees. And if I go to the calculator, then it's 7.15. So it's basically, it's already correct, but
Okay. Okay.
if you want, I can just change it to 7.14.
Okay.
It's not change much. So that's your central peak. And then you can use the same tool to measure the peak values for your black body radiation curves. For example, you can zoom on these curves and then you can measure.
I see. So you're just placing that on the peak and it gives you the numbers right there. The software does it for you.
And of course there is an uncertainty here, and then you probably want to estimate uncertainty as well when you do those calculations. So I'm seeing 1500 nanometers here, for example, 1560 nanometers, and then if I go to the next one,
That's for the wavelength?
yeah, and then I see 1626, and then I go to the next one. Hopefully it's going to be higher. It's about the same. So it looks like we are having some little bit of error there.
Yeah.
Experiment, and then it goes to 1656 on the next one. Yeah.
Beautiful, doctor. So is that's going to make everything clear to them what they're reading in there?
Yeah. So we might want to repeat that run one more time for the 6 volts, or was it 7 volts actually?
It looks like that's the 7-volt peak that
Yeah.
looks a little.
1611.
It's almost the same as the 8.
Yeah, and then so let's repeat that 7 volt peak to see what happened. Okay. So let's see.
Okay, you want me to change it back to 7 now?
Yeah.
I can do that with my free hand. Are you going to get it?
I can probably do it for you.
Okay. So the number on the left is the voltage on the filament. The number on the right, of course, is the current. The ratio thereof being the resistance. Okay, let me mount up on tripod again here in real time. And let me get in focus again. Let me film this one close. They know the apparatus is there. Let me actually film this peak being created up close so they can get a real. Hang on one second. I need camera focus. 1 second, please. Okay, go ahead and run your data. We'll see the curve be created here. No, this is the 6 volt again, or no, 7 volts. So he's rotating the sensor through the rainbow, and at some point we'll see the curve be created here. There it is. It's being redrawn over the former data. Looked like it changed a little bit, but not much, huh, doctor?
Yeah.
It almost drew directly over the old data with a different color, right? And then he's gonna find he's gonna find the zero. When the zero peak goes through, we're gonna see it on this curve on the left be generated here any second now.
Yeah, I think we went through it already. Okay.
Okay,
so
we didn't
that's
see it because we.
basically- it was blocked by.
It was
other-
there. It is.
Let's
There it
try
is.
that.
We had it tucked behind the other graph.
So
Sorry.
now let's zoom it on this graph see the teal color, this one here, kind of like aqua teal, looks like they work better actually. So if you look at the peak value here,
It did, it shifted, yeah.
Because the problem we were having, for example, for this graph here, for the upper one, we started around 15, and then we went up to, so let's see,
15 millimeters, is that right?
nanometer, yeah.
And so they,
then-
they can
and then-
convert that to nanometers.
No, that's nanometer, right?
Right, but they can convert it if they want.
You mean to like,
Nanometers or
oh,
whatever.
that's
yeah.
nanometer already.
Oh, it's already nanometers?
Yeah, so this 1611,
Oh, I'm sorry. Of course it is. I was thinking
Yeah,
it's 15 nanometers.
right.
Right.
1611 nanometers, and then now if you look at this one, now it's looking better actually. So it's around 1627, so it's higher now. So maybe actually 1650 maybe even.
Yeah.
So somewhere there.
Yeah, yeah.
Because earlier it was actually showing lower, which was
Right. Now, what do you think caused that error? Did you move too fast through the rainbow?
It's a good question. It's a good question. So it's hard to say actually, but we certainly had to repeat that. And then if you want to be really sure, then you want to keep repeating this. But looks like right now the curves are shifting.
Yeah,
Right
you can see lambda max is shifting to the right as the filament gets colder, right?
Right.
Which is consistent with what we expect. That's good. Oh, that's a beautiful. Okay, guys, in Physics 173, this proves quantum mechanics exists. Well, it proves that light comes in chunks, and then.
And by the way, guys, I'm gonna go ahead and delete run number 3.
Okay.
Which was the run that we had problems. So that's the previous 7 volts.
We'll do that again.
No, I mean we already done that. So
Okay.
So I'm just gonna go ahead and delete this.
Oh, you can delete the old data that wasn't shifted
right.
to the right for some reason.
And then what we could do, we could go to the data summary here, and then we could actually label these data runs properly. So you can just right click on those, I believe, and then rename. So I'm gonna rename the first one as 9 volts, right?
Yeah.
So 9 volts. So let's see if that's going to work. Okay, as you can see, it's now showing correctly. And then this one I'm going to rename 8 volts.
8 volts.
Okay, I made a typo there. Okay, and then run number 5 is actually 7. Typo again.
Yeah, because we repeated it.
So and run number 4 is going to be 6 volts, right?
Right, and then that's the data you're going to send to them.
Yeah. So oops, I keep pressing shift here. All right. Let's see. Yeah. All right. So now if you look at the graph here, it's showing the run numbers by the voltage. So it's 987. So this one is like green one is 9, and then darker green is 8. And
Beautiful. That's beautiful.
And then the other thing you want to look at here is the if you make a graph of the temperature. And then
Is that a function of time there? That
Right.
horizontal line. So the
Yeah.
filament's maintaining at a constant
and
temperature.
then I'll show you how to show all the data together here. You see the icon here, which is data icon, and if you click on it, and then you can choose all voltages here, 9, 8, 6, and 7. Now these are the temperature values for 9 volts, 8 volts, 7 volts, and 6 volts.
Right.
So now you can verify the Wien's displacement relationship
With those numbers.
with these numbers compared against the values you get from the peak values
Right.
and the formula.
That's it. That's beautiful.
So now you need to do all the analysis, which is there's plenty of analysis to do for you, basically using this data.
Thank you, Doctor. I'll make one more comment. These curves, these blackbody radiation curves here, are not proving all of quantum mechanics. I mean, it's showing you that the energy, as you increase the to increase the energy, it comes in chunks of Planck's constant times the frequency. Well, if you're at a given energy, it'll only go up in chunks of Planck's constant times a change in frequency. So it's not a continuous function. It tells you that there are photons in there, or little bundles of energy. Now, the fact that the energy is equal to Planck's constant times the frequency, which is the Einstein relation, you really need the photoelectric effect to manifest that experimentally, that the Einstein relation is h times the frequency. The energy is h times the frequency. Okay, you want to say anything else?
Oh, well, thank you, Professor Burke, for helping me with this. By the way, you're a professional filmmaker, right?
I am, and so you're seeing filmmaking in action here, right in the lab.
Well, I hope it was entertaining, and I hope you have fun analyzing the data.
See you guys.